Hello, can you listen to me? Hello. Okay, so let us start today. So in last class we have seen this linear associator, and we saw with one problem that whenever you have some noise in your data, linear associator is not good solution. So we need some kind of thresholding, as we saw in last class, so that we can retrieve data even if we have supplied with some noise. Now, recurrent networks are, you can say, a next step to that, where we have a single layer of neurons with feedback. So this is a new concept. Till now we have not seen anything like feedback. Now the Hopfield network, if you see, which is in front of you, this has some neurons. So these are all neurons with a function, activation function, which is a sine function. So it produces +1 or it produces -1. So whenever net is greater than 0, it will produce +1. Whenever net is less than 0, it will produce -1. So that kind of activation function is deployed here. Now you see this unique thing. This is output of neuron number 1. So let us call this as V1. This is fed back to the circuit like this. Okay, so it is coming back like this, and it is distributed to neurons other than from the neuron where it is being taken back. So you don't have any connection to this first neuron from where you have taken the output. Okay, so this self feedback do not exist. So this is important thing. Self feedback is absent. You take any neuron, you will see that its output, suppose I take this V2, output is fed back, it is coming here as V2. So this V2 is here, and it is distributed to all neurons except this neuron. Okay, so there is no connection. You can check for the last one also. So this is Vn coming here as Vn. So there is no connection to self itself. So self feedback do not exist. So keep this thing in mind. Self feedback do not exist, and you have a feedback loop. So output is coming back as input. So that is the unique thing of this network. So this is something like energy based system. So we will see the stability of this system in the form of energy, and you will see how this stability is used to store the patterns. So storing of the pattern happens with the help of, say, energy. Now this is one thing, that is, there is a self feedback absent, and actually there are feedbacks without self feedbacks. Now this is a connection I1, I2 up to IN. These are initial inputs. So whenever you start your network, you can provide some kind of initial input, so that you will provide here. Okay, and you can see here the terminals T1, T2, and so on up to Tn. with negative or -1 connection. Okay, so weights are T1, T2, Tn, and input is fixed to -1. So these are all bias connections. So given a neuron, say this is neuron, you have initial input, you have feedback coming from different other neurons, and a bias. So whenever you have a net value here, say net 1 greater than 0, this will be producing +1. Whenever net 1 is less than 0, this will produce -1. So these things you should remember. So this is +1, -1. So if suppose I say this is a three-dimensional or three neuron structure, you can see that I have something like this. Okay, so the bottommost point here would be -1, -1, -1 for all the neurons producing -1 outputs, and the top point will be +1, +1, +1 when all neurons are producing +1. Okay, so you can see that my output is always one of the vertices of this box. If it is a 3D case, then it will be either this point, this point, or this point, or this point. All corners of this box, one of them will be the state of this network. Okay. Now what is basic idea here is, suppose I want to store suppose pattern +1, +1, +1 in this network, then I should create at this particular point a point with minimum energy. So this system is like a dynamical system with feedback, and it has some kind of energy. We will see that equation. So the idea is that I should create energy minima point here, a stable point here, so that with some initial guess, I will land to this minima. Okay, suppose I am starting from this point, then I will be pushed, I will be losing my energy and land to this point. Say I am standing here, then I will go in this direction somehow, and then I will land to this minima. So this point is attracting the state of the machine, and it will be settling down here. So whenever you reach to this point, which is the minima energy point, you will not escape out of this. Okay, so that is the idea. So when I want to store +1, +1, +1, I will create at this position a minima, energy minima, say energy minima situation, so that I will not escape out of this. Whenever I land to this, I will remain in this. Now this is possible with the help of adjustments of weights. What is in my hand? In my hand I have weights. So I have to design the network such that these weights are producing minima here. Okay, suppose I want to store this pattern, then I should create a minima at this location. So like that we can store the patterns using this Hopfield network. Now net value that is coming to a neuron can be given by net I is equal to a summation j equal to 1 to n, so that is all the inputs, wij all the inputs connected to ith neuron multiplied by Vj, the input. But here you will see that J is not equal to I. So this is all about the feedback. Why J is not equal to I? Because self feedback do not exist. Okay. So weight Wii is 0 or Wjj is 0. That's why here J is not equal to I. For other values where J is not equal to I, there exists some weight. Okay. So that is the structure of this network. So this is accumulated, or this is you can say demonstrated here with this form. Now plus initial input minus threshold. So that will give you total net value of a neuron. Now where I is equal to 1 to n, that means I have n number of units in my structure. So how many units you will put? It depends on what is the length of feature you want to remember. Suppose I want to remember a big vector like this, okay, maybe plus 1, minus 1, say minus 1, minus 1, minus 1, plus 1. Okay, I want to remember this 1, 2, 3, 4, 5, 6. That means my pattern length is 6. So I will require n equal to 6. So I will require 6 neurons in total. So there will be in a single layer. Okay, so this becomes single layer, and whatever is output coming out here is taken back. Okay, so all this output are coming back. And what is the caution, or what is the precaution one should take? Don't connect this feedback to the neuron itself from where it is coming. So this connection you have to remove. Okay, so this is my weight Wi for a given neuron, and this is the input V. So when I want to write this in the form of, say, matrix, all the weights, so this is my W matrix, and this is the weight associated with neuron 1. This is the weight associated with 2, neuron 2, and this is weight associated with neuron N. Okay, so you can observe this diagonal is 0. So Wij is equal to Wji. So this is a speciality of this network. This weight matrix is symmetric. So whatever is W, suppose I take W12, then this is equal to W21. So W31 is equal to W13, or W35 is equal to W53. So all these weights are symmetric. So why this is like this, we will see next. So what is the speciality that of this weight matrix? So these weights of diagonal elements are of same value. Okay, this will be same, these two will be same, these two will be same, and so on. So this matrix is symmetric matrix. Second important thing, diagonal is 0. So this is a typical case intentionally done. Now this network has special rule to compute its output. It's not like our earlier network that you will feed some input and you will calculate output directly. Okay, so that is not the case here. Now we will see how we can compute output. It has a special method to compute output that is called as asynchronous output calculation. So what it means? It means that only one node at a time is randomly selected to update its state. So all the neurons are not allowed to change their states in one go. Okay, we have to choose one of the neurons randomly and allow its state to change. Then take second neuron randomly and allow its state to change. Like that, initially we can make a sequence before I do something or before I start the calculation. Suppose there are 5 neurons. We first of all decide a sequence, number sequence. Let us say first neuron first, then third, maybe fourth, maybe fifth, and then second. Say this is my sequence. This is totally random. You can have your own sequence. Okay, so what it means is that there are 5 neurons, 1, 2, 3, 4, 5. Then I will allow this first neuron to change its state first. So there are outputs coming like this, and it is feedback, and this is also feedback. Okay, so this is like this. So given the state v vector and initial vector I, we will feed this to the neurons, all the neurons, and then only first neuron actually is allowed to update. Then this updated value is taken back, and then we allow third neuron to change its state. Then we allow fourth, then I allow fifth, and then I allow second. Okay, and this updation will repeat. So after allowing all of them one by one to change their state, one step is over, but that is not the final output. Okay, so what we do, we allow one more time all of them to change their state as per again this sequence. Okay, and we keep on doing this repetition of calculation of output till the output is stable. Okay, so what happens is, suppose this is some v0, the initial say input, that will result into some, I should take say uh, 5 neurons, because our example is of 5. So let us say this is +1. So this is my initial input. Then this first bit is updated. Maybe this has produced -1, and all others are same now. You can observe only this has changed. Now this will be fade again, and suppose I allow now neuron number 3, this one to change. And suppose this has not changed. So this has remained as it is, and I have completed the sequence updation. Then I take fourth, then I take fifth, then I take second. Like that, I will allow everybody to change its state one by one. Once all neurons are exhausted, so my updation is over, that is first step. Then I will repeat exactly same again. Now suppose after such let us say 15 steps, v15 is equal to v16. So there is no change at all. Even if I do for all the neurons, that is 15th step and 16th step, it means that I have updated all 5 neurons here, and then I have updated all 5 neurons here, but outputs are remaining same. There is no change. Then I can stop. Okay, So it's like that. This is my input, initial input, then I take output, it is fed back, then I keep on changing say states. I allow to change the states of individual neurons. I will stop at a position when this new vector is equal to old vector. There is no change. Okay, that means my circuit has stabilized to certain stored pattern. Okay, so this is going to happen. What happens is there is some energy in my network. When I iterate like this, my energy keeps on losing, and then I will settle to some particular point, particular minima, and then I don't have energy to lose. So my network will halt at that position. Okay, and that is the position where I have stored the pattern, which I want to remember. So this is how this will work. So what is working principle? If the increments of certain bounded positive valued computational energy function under above update rule are found to be non-positive, then the function is called Lyapunov function and system would be asymptotically stable. So we will see details of this. This is the working principle on which this is built. So this is also known as asynchronous stochastic Hopfield recursion. Now to understand how it works, we need to brush up our fundamentals about dynamical system and its stability. So we will not go into details, but we will see how it is used in this network. So a dynamical system consists of state space whose coordinates describe the state at any instant, and a dynamical rule that specifies the immediate future of all state variables, given only the present values of those state variables. What it means is, if I say x is a vector of state variables, then it consists of different variables like xn, x1 to xn. So these are the coordinates of state space. Suppose I take a 3D case, then x1, then x2, and maybe x3. That will form the state space. Now what it says that there is certain rule, dynamical rule, that specifies immediate future of all variables. Suppose I am standing here. So this is some point P defined by some x1, x2, x3. So system is at this position. Now with the rule that is defined, dynamical rule, my point may go to this position, say P dash, which has the coordinate x1 dash, x2 dash, and x3 dash. Okay, so from P to P dash, this system has moved with respect to some time variable. So variable, that why this is called a dynamical system, because time is the key thing. So there is existence of a time variable. So after certain amount of time, so your system will move from this position to this position. Okay, and I can predict that system will move from P to P dash if I know the present values. Present values means present values are x1, x2, x3. So that is given to you. Then you can predict what will happen to these variables in next future, next immediate future. provided you have a dynamical rule. Okay, so for example, you have like a pendulum. You have, say, this is a pendulum moving like this. Okay, so there is some angle theta, and you have some angular velocity with this pendulum. So if I provide you the current position and then angular velocity, that is angle and angular velocity, then you can estimate with the help of Newton's simple law where this next position will be. So that is how this dynamical system are. So implication is that there is a notion of time, and that a state at one time evolves to state or possibly a collection of state at later time. So once you know, suppose initial state P0, then you can predict P1, P2, and so on with respect to time, what will happen to your machine or what will happen to your system. Okay. So you have linear dynamical systems are those whose evaluation functions are linear. This variation can take two forms, either as a flow, so you are following this equation. So you have a differentiation of x state space variables with respect to time equal to some matrix A into xt. So this is kind of a flow, or as a mapping in which x varies in discrete steps, say x m plus 1 is equal to a into xm. So this is a linear case and this is a flow kind of, so derivative is involved. Now this is about linear dynamical system, but practically we face non-linearity. So non-linear dynamical systems are in mm, mathematics and science. A nonlinear system is a system in which the change of output is not proportional to change in input. Okay. So when there is a small change in x, say output is suppose y, there will be a small change in y. So it's not like that there is some, you can say delta y is equal to delta alpha into delta x. So there is not a linear relation. So this is not in existence when you talk about non-linear dynamical system. So this is a linear system. Okay, so suppose we are having a non-linear system which we face in general, then this equation do not hold. Now, in those situations, stability can be given by Lyapunov stability. So this is given by Lyapunov, who is a Russian mathematician. You can search about him. So this is quite old, I think, in 1911 or so. He was there. So it's quite old, but he has given the stability criteria for dynamical system. So he defines an equilibrium of a dynamical system is a solution that does not change with time. Okay. So suppose I say xc, that is a state of a machine when it is in equilibrium. So once your system is in equilibrium, it will not change this state space variable. So Lyapunov stability of an equilibrium means that solutions stating close enough to the equilibrium and remain close enough forever. So this is simple Lyapunov stability. We will see what is this. And asymptotic stability means that start close enough, not only remain close enough, but also eventually converge to equilibrium. Suppose this is your state variable right now, and say this is the equilibrium point. So you start with this initial point. So over a period of time, your system is just moving around this. Okay, it keeps revolving around this equilibrium point. Then this is Lyapunov stability. When your initial guess or initial say state space position reaches eventually to the equilibrium. So when you start with this position and you reach to the stable position, equilibrium position means once you reach this point, you cannot move, or your machine will not move from this point anymore. Okay, so here it's not reaching to equilibrium, but it is just around it. Okay, so you can understand the difference. In asymptotic stability, it will reach to this equilibrium. Okay, so if such kind of thing happens, then I can say that system is stable, and we are using this second thing in our Hopfield network. Now when you look at, say, energy of a system, you can find three things. One is local minima, the other one is global minima, and saddle point. Now global minima is this point in this diagram where your energy is minimum in global sense. So there is no other point of my system which is less than this point. Okay, when you take this other point, say this point, your gradients are 0. Okay, you can see the derivative of this and derivative along this axis is 0. So derivative along, say, x1 and derivative along x2 of this energy function is 0. How do I find out minima? I take gradient, or I take, say, partial differentiation with all the variables, and if that thing is equal to 0, then I say it's minimum. Okay, say this is along x1 axis, this is suppose x1 and this is suppose x2, then I take this partial differentiation. So this will be the point where derivative with respect to x1 and derivative with respect to x2 will be 0. So that point is minima. Here also same thing you will find, derivative along x1, derivative along x2 is 0. So what is global minima? If I compare these 2 points where gradients are 0, then you will see that energy here is minimum, compared to that energy here is higher. So we call this point as global minima and this point as local minima. Condition is your gradient must be 0. So both the points gradients are 0. Now there is one more point where again gradients are 0, but this is not a minima. Okay, so gradients at this point, even though they are 0, but along, say, x1 direction and x2 direction, they are 0, but it's not a minima. It is called as saddle point. Okay, it's called a saddle point, which is having gradient 0, but it's not minima. So you can stuck up to these points when you are dealing with a dynamical system. Your aim is to actually reach to global minima when you are dealing with some kind of a neural network structure. Say I want to have my error minima. So when I talk about suppose a classification problem, so instead of energy there it will be some error function. So I want to reach to global minima somehow, and I may stuck up, or my system may stuck up in local minima where it will find gradient is 0, or a saddle point where gradients are again 0. Okay, so we have to deal with this properly. Now this is an auto associator. Hopfield network is an auto associator. We will see details and a small derivation where you will see that energy is getting radiated in every step, or network is losing its energy in every step, and it is getting stable to a minima. Okay, so that we will see with one example in next class. So thank you for today.